Algebra 2 skills number 36, exponential graphs. So let's first talk about what a graph is. Remember, it's a picture of all solutions. So when you're looking at a graph, you're simply looking at all the ordered pairs that makes the given function true if you put all the x's in the x position and all the y's in the y position. So we'll see that here in a moment. But first, what's an exponential function? Exponential function is of the form a times b to the x, and there may be a little more to this, but a is going to be a real number, so no imaginaries at all, and b is going to be a positive number that is not 1. So we don't want our base, this b value, to be negative, 0, or 1. Okay, there may be other numbers in there, like you might see some adding and subtracting here, or adding and subtracting out there, but the exponent should be linear. Okay, so no x squares or x cubes in the exponent, and we should have a variable in the exponent. That's important. Okay, so let's see if these are exponential based on the definition we just looked at. Here we have a number. There's a real number there. And we have a number that isn't 0 or 1, and it's raised to a linear exponent. We have a variable in the exponent, so absolutely, this is exponential. Here we do not have a number other than a positive number other than 1 here. We have a variable, and we don't have a variable in the exponent, so that's no good. You have to have a variable in the exponent if it's to be exponential. Okay, a couple other examples. Absolutely nothing wrong with this. Again, you have a variable in the exponent. This is a good base. But this is no good because, we cannot have a 1 base. We don't want a 1, a 0, or a negative number in this position. Okay, so make sure we have a good base, and let's make sure we have a variable in that exponent, and that variable is to the first power. We then have growth versus decay is something to talk about. Again, here's your exponential model. Growth would be when that base is bigger than 1. Remember, it shouldn't be negative, 0, or 1. But if you're specifically bigger than 1, we call it growth. And if you're between 0 and 1, we call it decay. Okay, it's not exponential if you're anywhere else. So you're either bigger than 1 or you're between 0 and 1. And we have different looks based on where you're at. We do want to make sure our x term and our exponent is positive before making the declaration if it's growth or decay. So some examples there. Here, the base is between 0 and 1, so that's absolutely decay. On this one, don't worry about the number in front. Okay, don't worry about that. Also, you cannot multiply these. The order of operations states that the exponent must be resolved before you can multiply, so you only pay attention to the 2 that's bigger than 1, therefore it's a growth. Okay, on this third example, we do have to take care of this native exponent before we can declare. So if you remember your exponent rules, a native exponent is simply going to flip it upside down to 3/2. And though a fraction, 3/2 is bigger than 1, so this is a growth. So at first it looks like a decay, but again, make sure that negative has been resolved before making the declaration of growth or decay. Okay, so here's what the growth graph looks like. So if you have a base that's bigger than 1, you're going to have a graph similar to this. Notice it's very flat here and very steep there. So it's like it takes off, and when it takes off, it really starts getting steep very quickly. A decay graph looks very similar. It's just flat on the right-hand side and it's steep on the left-hand side. So it's like it was very steep and it's declining in value and then flattening out. What you may have noticed on those two graphs is that on the flat side, it looked like it sort of hugged a horizontal line. And we call that horizontal line an asymptote. In this case, a horizontal asymptote. An asymptote is a line that a graph approaches more and more closely but does not cross. Okay, so knowing all that, let's look at how you graph an exponential if you don't have a graphing utility. First, we want to place the asymptote. It's going to match the vertical shift. And this will make more sense when we see examples. But it's important to put that asymptote there just so you have a sense of where that graph should be molded, where it should not cross. So let's put that asymptote before anything else. We do want to take note if it's growth or decay based on our previous discussion, and be mindful of any transformation. So we'll talk about those through these examples. Here's an example of that. Graph until the domain and range. Okay, so here we have a clear exponential. We have a good base raised to a variable power. So first we want to look at this outside shift. This outside shift here, vertical shift, if you know your graph transformations, is at 4. So we want to make sure and put that 4, that purple dashed line in this picture, You want to make sure that's there before you graph anything else. Also, we note that this is a 2, therefore the graph is a growth. You're flat on the left and you're steep on the right. You also want to be mindful of other transformations. Note that that +4 has already been taken care of with the asymptote. There are other things that could happen, like a horizontal shift within the exponent, or you might have a negative out front that flips it upside down, but that doesn't occur here. The other thing to say for this before we get to domain and range is exactly how steep is it? Well, it depends on the size of the base. The bigger the base here, the steeper it is. Also, if you multiply by a number larger than 1, remember that's a vertical stretch. But for these exponential graphs, they all look very similar. It's hard to tell, just freehanding it, exactly how steep to make it. So that's not something that's emphasized if you're freehanding. Just wanted to make mention of that they do change in steepnesses somewhat. Now, with regards to domain and range, the domain is all the x values covered by a graph, as discussed in a previous video. So if you look, this green graph is going to go left. It's never going to cross that purple line, but it will go left forever, and it's still tending to the right forever. So we say our domain is all real numbers from negative infinity to positive infinity. Our range, meanwhile, is all of our y values. And you notice this graph will not go below the 4, and it also goes up forever. So we say 4 to infinity. But something subtle here. Notice that the 4 gets a parenthesis. That's because you're never actually going to touch 4. 4 serves as the boundary, so you can get down to 4.1 or 4.01 or 4.001, but you'll never actually get to 4. That's why we have a parenthesis there. A couple other quick examples, same instructions. This time we have this function over here. Notice that before we show the graph, it is a decay, so it's going to go the other way. And we do have a vertical shift down 1, so our asymptote should be 1 lower than the x-axis. There's also this 5. That's going to be a horizontal push to the right. So let's observe that. Okay, so here's your asymptote. Again, 1 below. Notice it's a decay. It's flat on the right instead of the left. That's because this is less than 1. And notice also that you're shifted to the right versus those parent graphs that we looked at earlier. Now, exactly how far do you shift it? Well, you shift it 5 units. And again, when you're freehanding, it's hard to know exactly where to put it. The best way to describe it is it sort of takes off. Instead of ordinarily it would hit at this 0, 1 above. And again, whether it's 1 above or not depends on if there's a number up here. There's a lot of little details here, but you kind of take off 5 right of the y-axis is a good way to describe it. But remember, when you're freehanding, getting it perfect is just not that important of a skill. We just want to take note of these transformations. Now, with regards to our domain and range, it's still negative infinity to positive infinity. It still goes left forever. It still goes right forever. That's not going to be affected by that 5 shift. So 5 does not show up here. It just simply moves the graph, but it still goes forever both directions. And the range, again, is -1. That's how low it goes, to positive infinity. That's how high it goes. It's never going to cross that -1 or even touch it, hence the parenthesis. Finally, example 3, we're going to get one that's flipped. Okay, this is a reflection. Also notice there's no asymptote shift here, so there's no big number on the outside. This is a horizontal shift. So we should see a growth graph that got flipped upside down and a leftward shift of 2. So you can observe that. Yeah, this is a growth graph. You remember this, if you vision this rather upside down, it would be a growth, but here it is going down. The asymptote did not move. It's still on the x-axis. That's because there's no number here. And there's a slight shift to the left. Now your domain and range, domain is still negative infinity to positive infinity because you go left forever, right forever. The range this time, remember, you have to list a smaller number first. All right, so your range, let me click correctly here, is negative infinity to 0, not the other way around. It goes down forever and it goes up to 0. The high number must be listed last. And again, it can't touch 0, therefore you get the parenthesis.